Hello, everybody, and welcome. Can you hear me okay?
Yeah. How you doing, John?
Awesome. How are you doing? Okay, so test coming. I hope everybody had happy Thanksgiving, happy holidays, and I guess today's a holiday, and some people would say today's a holiday. So you have an exam coming up on Tuesday, and I presume it is all about infinite series. So how can I help you understand that content today? Does anybody have a topic that they'd like to discuss, or perhaps a convergence test that they'd like to discuss, or perhaps a particular problem?
Yeah, I had one from the quiz, actually.
Perfect.
It was find the values of p for which the series is convergent. It was a
Ah,
sum from 2 to infinity of 1 over n, and then the quantity log n to the p.
like that?
Yeah, it was natural log, but does that matter?
Yeah. So natural log of n, and then that to the p.
Correct.
That's a great question.
Yeah, I missed that one.
Is there a value of p? Okay, so we have a lot of tests under our belt at this point.
It said find the values of p for which the series is convergent.
Right. Okay. Let me just check if anybody. Okay, so right, so we want to find p such that this converges. So that's a great question. So yeah, so for example, does if p were 1, does this series converge or diverge? Or if p were 2, does this series converge or diverge, or so on? So so let's see. So let's just think about this for a second. So natural log of n, right, as n gets pretty big, this gets, well, it gets big, but it gets big slowly, but that doesn't matter. So that's getting bigger. If p were larger, like if p were 100, right, that would make this quite big, which would make the denominator quite big, which would make each term quite small. And so as p gets larger, the terms get smaller, and it becomes more likely to converge. So I'm going to guess that the answer is something like p bigger than, I don't know, some value. I don't know what that value is.
Is it just where,
Or to some value.
quick question, is it
Sure.
just where L log of n to the p is greater than or equal to n, so that's 1 over n squared or more? Or that would be that, or the opposite?
That's an excellent question. So I like what I think you're getting at is you're comparing it to a p series, right? It is like if it were like this instead. Yeah, so recall that even that converges. Right? Remember that 2 is not the boundary between convergence and divergence. 1 is the boundary. So yeah, so when I first saw this series, my intuition was, okay, well, it's like n to the 1 plus a little bit more. So surely that's like n to the 1.01 or something like that. So surely that's convergent. But I was wrong. In fact, this ln grows so slowly that it is less powerful than this. I could rewrite this as like, right? It turns out that ln grows so slowly that it's less powerful than that. So even so that ln, if you just add an ln to the denominator, that's actually not enough to make it convergent. Believe it or not, that still diverges, which I found very, very surprising. But perhaps if you add 2 of them, or maybe 3 of them, or 4 of them, or 100 of them, perhaps that will be enough to make the whole thing convergent. I'm not sure. So let's give it a try with the ratio test. So the reason I suspect the ratio test is because it's, or the reason why I suspect the ratio test is going to work well is because it's like a really simple thing with a bunch of things just multiplied together, no addition or anything. So, so it should be relatively easy to take the limit of the ratio of this. So just as a reminder, the ratio test says that when you have a series like this, and and from whatever to infinity, the first, what the first term doesn't matter. That doesn't really matter. So I'll just say 1, but you can replace that with anything. The ratio test, it says, so take this limit, which is the limit as n goes to infinity of the ratio of 2 consecutive terms. And then don't worry if it's positive or negative. So you just take that limit. And then the ratio test tells you if L is bigger than 1, it diverges. If that limit is less than 1, it converges. But if, unfortunately, that limit is exactly equal to 1, then it does not know. The ratio test is not powerful enough to say, or you might say inconclusive. So let's see if this is a fruitful path for us. So we'll take that term. So the terms here are 1 over n times natural log of n to the p. So I won't put the parentheses there. Just understand that when I say to the p, I mean it's applied to this. So that's an. So that means the thing that we're interested in. My favorite way to work this out is just think of it as the next term times the reciprocal of the nth term. So that's going to be 1 over n plus 1 plugged into this. And p is some variable. I don't know how big that is. I'll just leave it as p. Times the reciprocal of the nth term, which would actually be this on top, right? So there. So that's the... Oh, so unfortunately, this isn't going to work out, is it? Because you end up with n over n plus 1 and natural log of n over natural log of n plus 1. And both of those are to the p. And if I'm not mistaken, both of those approach 1. That is very unfortunate. Yeah, surely those do both approach 1. Okay, so unfortunately, you do get a limit of 1, which means the ratio test is inconclusive. So the ratio test is not going to work here. Okay. So something else then. Find p such that this converges. Let me look at a list of all the tests you guys have. So it satisfies the nth term test. It's not a geometric series. It's not a p series. Perhaps we could try the integral test. Oh, actually, yeah, that's exactly it. Right, so the integral test, right, says you can replace this. Right, this has the same convergence or divergence as this. Now, I think this integral is actually quite doable. We can simply say let u be the natural log of x, And that's gorgeous because that means that our du gives us that extra x that we need to get rid of. So it turns out that we are looking at 1 over u to the p du. And then the bounds, well, if x is 2, then u would be the natural log of 2. So I'll take the bounds with me here. And again, we really only care if it's infinite or finite. So you don't really need to worry that much about the specific numbers. You just need to figure out, is it infinite or not? So let's break this up into a couple different situations here. Remember, we can do a thing like this is really u to the negative p, right? You can write it that way too if you wanted. You do an integral like that with the power rule all the time, unless p is exactly -1, or excuse me, +1, I suppose. Maybe I shouldn't rewrite it like that. I'll just keep it like that. Right, so if u is exactly +1, excuse me, if p is exactly +1, then that works out to be the natural log of u, right? From infinity to ln of 2. And natural log of infinity is infinity, right? Or I should say natural log of b as b approaches infinity is infinity. So it diverges in that case, right? We can see that when p equals 1, it diverges in that case, because in that case, the integral works out to be the natural log. But for other cases, if p is not equal to -1, well, then it's not natural log, it's just the power rule, right? So let's see, that's integral of u to the negative p. So if we use the power rule, that should say increase the power by 1 and divide by the new power. So it's going to be u to the negative p plus 1 divided by that new power. Okay? And then that's from natural log of 2 to infinity. And so as usual, what we really mean by that is we'll take the limit as that upper bound approaches infinity, and then we'll plug in that upper bound. So, but then we just plug in natural log of 2. So as usual, we only care, is this infinite or finite? This part is clearly finite, so we might as well just ignore that. What we're really interested in is what's the deal with this? Does this thing go to infinity, or does it become finite? That will determine whether this converges or diverges. And of course, that depends on the value of p. For example, if p were, let's say 5, then we'd be looking at b to the -4 over -4, right? And as b approaches infinity, infinity to a negative power is 0, right? Because in a way that's really 1 over b to the 4. And indeed, as b approaches infinity, that goes to 0. But if p were something else, if p were, let's say, -3, well, I'll do a different, let's say -5, then that would be b to the +6 over 6, right? And indeed, that does go to infinity as b goes to infinity. So this thing has two options. It either goes to 0 or infinity, depending on the value of p. So can anybody tell me what is the boundary value? Like what's the, so here I picked a positive number, here I picked a negative number. What's the value right in the middle where between this converging and diverging? Because really what it comes down to is, does this b end up in the numerator or in the denominator?
So less than 1, it's going to converge.
Exactly right. Exactly right. So if p is less than 1, then Or wait a second. Oh yeah. Okay, that's right. So if p is less than 1, then this is going to be negative, right? Like if it was 0, for example. Wait, no, why am I, hold on, why is this confusing? If p is exactly 1, then that's negative 1 plus 1, so that's 0, right? So if p is less than 1, then that ends up positive, right? So let's split this up.
Now, if p is less
Let's
than
maybe
1, the numerator or the exponent will be negative, which will throw it to the bottom.
right, so if p is less than 1, then the numerator will be negative, indeed. Right.
The exponent of the numerator.
The exponent of the numerator, indeed. Something's not sitting right with me about that. Hold on, give me a second. If p is negative, because look, no, that's not true. Look, if p is negative 5, then it works out like this, right? It works out like it'd be negative 5 plus 1. So that would be, so if p is less than 1, that means negative p plus 1, the exponent, is positive.
Right, it's got to be greater than 1 here. Yep.
Right. So if that's positive, then we're talking about b to some positive number over some other thing, whatever. So that definitely is going to infinity, right? If p is equal to 1, then well, if p is equal to 1, then this is 0 in the denominator, so that's no good. But fortunately, we don't actually.
That was the other path.
We don't actually. Exactly. So we already accounted for the path where p equals 1. So we're on the path where p does not equal 1. So we don't have to worry about that. If p is greater than 1, well, then that means the exponent is going to be negative, which means it's going to be b to some negative number over something, which is the same as 1 over b to a positive number, and then some other stuff, who cares? That goes to 0, right? So in the case where p is less than 1, the integral of 1 over x times natural log of x to the p, it turns out that this is infinite, and thus that means that it is also the case that this series is infinite. But in the case that p is greater than 1, it turns out that that same integral, sorry, I should have said 2 to infinity. That same integral is not infinite. Now, I don't know what it is. I don't even care. But that means then that the series then must be less than infinity as well. So indeed, so it depends on the value of p. But we just concluded that if p is bigger than 1, it's convergent. Divergent. And then we really should inspect the case where p equals 1. So what happened when p equals 1? Well, that worked out to be infinity then too. So it's divergent in that case as well. So there you go. So this is convergent for p greater than 1 and divergent for p less than or equal to 1. Yeah, and the trick to that was the integral tests, right? Swapping it out for an integral that we have all these techniques to handle. I was wrong to think the ratio test. The ratio test worked out to be inconclusive because all the ratios were 1, so that's no good.
Cool, thanks.
You're welcome. All right. Welcome, Nolan. I hope you weren't waiting there too long. Sorry, I was on the whiteboard, didn't see what was going on here. Okay. Anything else? How can I help you guys next? That was yeah, that was this one problem. I think I've asked this before. But when I am in the whiteboard, can you still see my camera? Because it disappears for me and it disappeared in the recording. That's weird because it disappears in the recording. Interesting. Well, that's probably bad because I probably have my hand on top of it like a lot. Sorry.
Yeah, I don't think I saw when you were just doing the whiteboard a minute ago. I don't think your video was up there.
Oh, okay, huh. All right. Okay. What is this telling me about? I don't know. Why is there? Oh, it's from the chat. I see. Q4 of quiz 3. I think 4 is in the numerator. Right. So if Arvind, if that was the same question as Brian's, yeah. So what's cool is if there's like a constant multiple times the whole series, or if there's like a 4 in the numerator, it's really a 4 times the entire series, because you could imagine a 4 distributing into all of those terms. So it doesn't actually affect anything, right? If it was finite, then if you multiply it by 4, it's still going to be finite. And if it was infinite, then if you multiply it by 4, it's still going to be infinite. So you can literally completely ignore constant multiples when it comes to the question of convergence or divergence. So it doesn't matter if I missed a 4 in the numerator there. Okay. Any more questions?
I had another one. If there's, unless someone else has one, it was for the it was the sum of a telescoping series. I'm not sure how I summed it up wrong, but it was a summation
Okay.
from 5 to infinity of 8 over n squared minus 1, which I just turn into a polynomial and then tried to solve for it, but I got the wrong fraction for some reason.
Okay, so I think you're quite right to suspect that this is a telescoping series.
Yeah, I mentioned it gave that hint in the quiz. So.
Oh, okay.
When I started getting rid of the terms, I'm not sure what I missed.
So did you start by trying to break this down into partial fractions?
Yeah, I took it to partial fractions and then started, and it took like several, I had to take it out like several terms to find out where I was repeating. But then I thought I captured them.
I'm not sure what you mean. So perhaps we should go. So should we go through this? The decomposition?
Unless someone else has a question they want to do first, it's fine as well.
Yeah, that would be totally great. There are 5 people here. So if anybody else has anything they want to talk about, we will do that. I will come check in a second. Okay, here we go. So this telescoping series. So yeah, so in fact, written this way, it may not be clear how this is telescoping, right? This would be 8 over 25 minus 1 plus 8 over 36 minus 1 plus 8 over 49 minus 1 plus 8 over 64 minus 1, and so on. 64 minus 1. So written this way, it's not clear how this is telescoping, right? So the trick is to rewrite it using partial fractions, and perhaps we will find out. So,
hey John,
sure.
quick question on that. Kind of philosophically, how can it be written 2 different ways and function 2 different ways? I mean, I see that it does, but it's just kind of strange. I know when you break it apart, it'll become a telescoping series, but this way it obviously doesn't. So it seems like it's almost like 2 different problems with the same. It's a dumb question.
No, that's not a dumb question at all. I'm not sure how to answer it though. So, we're only writing the numbers down in 2 different ways. The numbers are still the same values, right? So let's break it down first, and then we'll talk about that.
Okay.
Okay, so yeah, so we want to, so as usual, right, if we know that the denominator can be factored as n plus 1 times n minus 1, then it is guaranteed that there exists some values of a and b such that these things add up together to make that, right? So we just got to find what those are. That is the method of partial fractions. So the trick to finding out what those are is to clear the denominator. So we'll multiply both sides by the full thing, right? So we'll multiply both sides by this. No, by this. Now, of course, that cancels over here. But when we multiply over here, only some of them cancel. And you're left with some still, right? So this would work out to be nothing but 8 on the left-hand side. And on the right-hand side, a times n minus 1 plus b times n plus 1. So there's a couple ways to go ahead and work this out. One way is to just distribute everything and then collect terms by their degree. So put all the a terms over here, and then all the constant, put all the n terms over here is what I meant. And then, whoa, that was weird. Never seen that happen before. And then put all the constant terms at the end. So based on this, it must be the case, right? We see that the n terms must add up to be the n terms over here, right? So that's to say they must add up to be 0. And then we see that the constant terms must add up to be the constant terms over here. So we see that they must be 8. So in other words, we can extract a system of equations that a and b must add up to be 0, and that a and b must subtract to be 8. Okay. So with this system, we could perhaps add both equations together, and we'll get 2b, the a's disappear, equals 8. So that tells us that b must be 4. And then this first equation here tells me that a must be negative 4. Yeah. So I hope that makes sense, right? That's how we can find out that yeah, so I wrote it like this. I wrote it as a over n plus 1 plus b over n minus 1. But since a turns out to be negative, honestly, it might be better if I flip them around. So instead, I'll write it as it turns out that this 8 over n squared minus 1. So instead of putting the a one first, I'll actually put the b one first. Right, so same thing as we had up there, I just put them in a different order. And the reason I'm putting them in a different order is because it turns out that this one is negative, and I find it easier to think about if the second term is the negative one, because then I can simply write it as a difference like that. So yeah, okay, so with that in mind, what we're saying is that each of these fractions, each of these terms in the original one is actually separable into 2 smaller fractions, right? So every single one of those terms is actually the difference of, so this was n equals 5, n equals 6, n equals 7, n equals 8, n equals 9, and so on. So each of those terms can actually be split up. Let me move this. I'll just put it over there. Right, so each of those terms can actually be split up according to that. So this first term, instead of just writing it as a single fraction, as 8 over 5 squared minus 1, well, according to this, I can also write it as 4 over 5 minus 1 minus 4 over 5 plus 1. So I can take that term, 8 over 24, according to my partial fraction decomposition, that is the same as 4 over 4 minus 4 over 6, right? plugging in n equals 5, right? 4 over 4 minus 4 over 6. So that first term is totally the same. So I'm simply writing the same exact number in a different way, right? This is really 1/3, and this is really 1 minus 2/3. So that's also 1/3. So those are exactly the same quantity. And of course, there are infinitely many ways to write out that one single quantity. Actually, no, that's not true. There you go. Boom. There's infinitely many ways to write out that single quantity. We are just choosing a slightly different one from what we started with. The next term would be, so we could write it, one totally valid way to write it is 8 over 6 squared minus 1, or 8 over 35. But we have discovered that another way to write it would be 4 over 6 minus 1 minus 4 over 6 plus 1. So in other words, 4 over 6 minus 1 minus 4 over 6 plus 1, like that. Now, if you were to work this out, if you were to sit there and find a common denominator and subtract them and get like a single fraction, it would work out to be 8 over 35. Those are precisely the same quantity, just written in two different ways. And indeed, there are infinitely many ways that we could have written that quantity. These are only two of them. So we have not changed the numbers. We have not changed the size of each term in our series. We have only changed the symbols that we are using to express those terms, right? So let's keep going here. The next term would be, 4 over 6 minus 4 over 8. 4 over 7 minus 4 over 9. 4 over 8 minus 4 over 10, and so on. So again, each of those terms, if you were to sit down and do the work of combining those fractions together, it would be precisely the fraction above, because they are literally the same thing for all values of n, right? So all of those terms are completely unchanged by splitting them up. The only, the series itself is completely unaffected, but we, the people who are using the symbols, do reap a benefit, right? Because, now the symbols do this funny thing that they do, that they match up with each other, and many of them cancel each other out. So yeah, so you see that what happened in this case when I only went up to 9, that these first two pieces here survived, everybody else disappeared, and then these two last guys at the end survived as well. And perhaps you can see how that's gonna work in general, right? If we went maybe a couple more here.
Yeah, no, I understand now, and I see how it. Yeah, there's some more questions, so I got this. We're good.
Okay.
And I understand philosophically why it works now too.
Okay, awesome. So yeah, so we're merely changing the symbols, right? But
Yeah.
but in this language, it's like so clear how it all cancels itself out. Yeah,
Cool.
really quite spectacular.
Yeah.
So I can see that these remainder pieces are going to go to 0 as n goes to infinity. So that means that the sum must be these first two survivors.
Yeah.
Okay. Chat. Hello. How do we know A and B are 4 and -4 instead of like 5 and -3, for example? Great question, Nolan. I hope I didn't literally just erase the thing that would tell you that. Darn it, I did. Let me write them back again. So we got these two equations for A and B, right? That A plus B is 0 according to the n terms, and also B minus A is 8. So Nolan asks, how do we know that it's 4 and -4 instead of 5 and -3? Well, because only 4 and -4 simultaneously you add them to make 0 and you subtract them to make 8. Those are the only two numbers which will satisfy both of those equations at the same time. So for example, if you had 5 and -3, it's true that they subtract together to make 8, but if you add them together, it makes 2, not 0. So that's how you know that that it's got to be those two numbers and not any other two numbers, because those are the only two numbers that do both of these at the same time. Okay, Aravinda, yes, absolutely we can. Could you please tell me what that is? Either in the chat or with the mic. Oops.
I can read off to you for question 5.
Oh, sure, yeah, that'd be great.
It was find the radius of convergence R for the series, and it's a summation from n equals 3 to infinity of the fraction x to the n plus 2 over 5n factorial. 5 times n factorial.
Like that.
Yeah.
Okay. Right. I'm gonna go ahead and guess infinity, but we'll find out. So radius of convergence, right? So just for a bit of philosophical discussion, right? This series encompasses infinitely many infinite series, right? For example, it encompasses this one. It encompasses it encompasses this one. And it encompasses this one. Right? All of these are just the same series where x has taken on different values. Right? So all of those series are sort of encompassed by this single one where x is allowed to take on different values. Now you might imagine that depending on the value of x, perhaps some of these converge. And I'm just making this up. Don't and maybe some of them diverge, possibly. Right? It depends on the value of x, right? For example, in this one, I think it's pretty safe to say that it converges because your denominator is enormous and your numerator is staying what it is. And the same thing for this one. It's really the same thing, except some of them are negative. So of course it will converge even harder. But in this case, you see you have a numerator which is growing exponentially, and perhaps that's powerful enough to overcome the denominator and make the whole thing diverge. I'm not sure. So that's the idea is, which values of x cause the thing to converge and which values of x cause the thing to diverge. That's the whole idea of the interval of convergence, is which values of x cause it to converge. So in order to figure that out, all we need to do is apply some kind of convergence test while leaving x as a variable, and then figure out, what values of x are going to cause that convergence test to work out and which ones do not. So low key, in a question about interval of, radius or interval of convergence or whatever, it is almost always the case that the ratio test is your friend. Now, I do say almost always, there's always, exceptions, whatever, but usually it's the case that the ratio test is the way to go. Now, hold on a second. Okay, I'm fine. Okay, so let's apply the ratio test to this series. So we'll take the n plus 1th term. Right, so if I plug n plus 1 into these things, and then divided by the nth term. So I'll just take the reciprocal of the nth term. Like that. Absolute value of the whole thing, although that's not really going to matter in this case. I guess it does. I guess x could be negative. And then we'll take the limit as n goes to infinity. And we'll give this a name just so that we have a name for it. Okay, so we want to see what's the deal as n goes to infinity of that. So the trick is to simplify this whole thing, and you can simplify it quite a lot. So for one thing, the 5s can cancel each other, so that's not going to matter at all. you have a bunch of x's up here and a bunch of x's up down there. You've got exactly one more x on the top than on the bottom. So that means they cancel out to leave exactly one x on top. So that's the deal with that. These cancel all of these except for one, is one way you could see it. And that's of course regardless of the value of n. That's the whole beauty of it. What about the factorials? Factorials cancel out in a rather funny way, right? So that's n factorial over n plus 1 factorial. So for example, maybe something like 6 factorial over 7 factorial. So I hope you are familiar enough to know how this actually cancels out. To be 1 over 7, right? The factorials cancel each other out like that. That, n plus 1 factorial is just one step further than n factorial. So they mostly cancel out completely, and the only one who survives is that very last piece of it, right? So perhaps you can see how in general, n factorial over n plus 1 factorial, the exact same thing happens. All of n factorial cancels on the top and bottom, leaving only the very last thing there, right? Leaving only that n plus 1. So that's how these cancel out. And this is absolutely fantastic. We want to take the limit of this as n goes to infinity. Now, if n is going to infinity, right, the numerator is unaffected by n. That just stays x, whatever x is. So maybe x is 0, maybe x is 100, maybe x is -4. X could be anything. But fortunately, in this particular problem, it doesn't matter what x is, because no matter what, the numerator is going to infinity. And so this whole thing is going to 0. Boom. So in these kinds of problems, it often, whether this goes to infinity or 5 or 0 or 1 or whatever, depends on the value of x. But in this problem, we see it does not matter what x is. X could literally be anything, and this whole term is still going to go to 0. So it does not matter what x is. The ratio test always gives you a limit of 0. So recall that the ratio test, where did I write all that down before? Here it is. The ratio test, if that limit is less than 1, then it converges. So we see that in this case, we ended up with a limit of less than 1, which means it converges for all x. So the interval of convergence, right? What are the values of x such that this series converges? So let's actually go back up to here. It turns out that this is wrong. It turns out that it converges even when x is 10. It in fact converges for all values of x. So that's kind of an interesting lesson, right? It seems that even a numerator which grows exponentially, 10 to the n, right? That is extremely fast growing. It's going to become enormous. But it turns out that even exponential growth is not enough to overcome factorial growth. Factorial growth is so extreme that a factorial in the denominator will cause convergence even in the face of an exponentially growing numerator. So factorial is extremely powerful. If you've got a factorial in the denominator, you're probably going to converge. You should always confirm that with some kind of test or whatever, but that's a good thing to think. If factorial in the denominator, that's very strong. You've got very big denominators, you're probably going to converge. Uh-oh. Headphones just died there, so I hope you can still hear me. Can you guys still hear me?
Yep, you're good. Yep, you're good.
Okay, great. All right. So yeah, so it converges for all x. So the interval of convergence is which values of x does which values of x does this converge for? Well, it turns out all of them. And then the radius of convergence is simply the, half the length of that interval. So like if you were in the center of the interval, how far do you have to go to reach the outside? That's what radius means for a circle or a sphere or whatever. But in this case, it's an infinitely wide interval. So the radius of convergence is infinity. So there you have it. So in other cases, we might have come to a situation where whether this converges or diverges actually depends on the value of x. And then we could think through that, okay, so if x is this, then it's going to work out like this, and that's less than 1, so it converges. But if x is this, then that's more than 1, so it diverges, and so on. But in this case, it actually didn't matter. So the radius of convergence is infinite. Sorry, Nolan. Yeah, so the ratio test is this, right? It says take this limit, right? So the ratio of two consecutive terms, see what's the deal with that as n goes to infinity, and then if you know for sure that that's bigger or smaller than 1, then the ratio test can tell you exactly what's up. Unfortunately, though, sometimes you run into this case where the ratio test is not powerful enough to tell you what's going on. But fortunately, that didn't happen. For us, we got 0 for literally all values of x, so that means it converges for literally all values of x. So that's great. Yeah. So generally speaking, when you're given one of these interval of convergence or radius of convergence questions, the ratio test is your best friend. And it turns out in this case that they all converge for all values of x. Okay. Man, I feel. Yeah. Okay. Perhaps we have time for one more question. So if anybody would like to ask one, that would be great. I will be right back. Uh-oh. Oh, geez, I forgot I was plugged into that. Right. Oh, that's right. Okay, hello everybody. Is there anything else I can help you with before we leave for today? Oh yeah, there you go, Brian. Summation, 1 to infinity, -6 to the n, x to the n. Okay, so you are correct about that interval of convergence. What is the sum of those series for those value of x? I said 0. Right. Well, it depends on the value of x. So you're quite right with that interval of convergence. So let's pick a yeah. So it's n equals 1 in -6. Oh no. -6 to the n, x to the n, right? So I'm assuming, Brian, you went through the ratio test and you found out that that limit was less than 1, as long as x is within this interval.
Yes, yes.
You are quite correct. That is the interval of convergence, and so notice that that is centered around 0 with a radius of 1/6, right? So if you wanted to express this in terms of the radius of convergence, the radius would be 1/6 because, you know, I just want to belabor this point a little bit because some people find this confusing. I certainly did. The interval of convergence is this, you know, this interval on the number line. The radius of convergence is this distance between the center and the outside, which in this case, it's easy to see because the center is 0. That distance is 1/6. Right? So the interval of convergence would be that. The radius of convergence would be that. Okay. So the question is, what is the actual sum of the series in the cases when it converges? Yeah. So, like that. All right. Still not super used to this thing yet. So indeed, so this series converges or diverges depending on the value of x, right? If x is 1, for example, then this series is literally the sum of the powers of -6, right? So that would be like -6 plus +36 minus 216 plus whatever's after that. So that's definitely, those terms are getting bigger, and so certainly that diverges. In fact, it diverges from most values of x. That would be basically 18.
Oh, is this answer just one then?
No, so it depends on the value of x, doesn't it? For example, if x is so I'll pick something inside the interval of convergence this time. How about 1/12, for example? So -6 to the n times 1/12 to the n. Or you could rewrite that as since those are both to the n, you can multiply them together inside the parentheses there. That's -1/2 to the n. Now that converges. Well, what does it converge to? Well, in that case, it's the nice thing about this is a geometric series, right? Which is to say, each term is just a certain number times the previous term, and in this case, it's -1/2. And we know we have a formula for the sum of a geometric series. So if this is something times something else, right? Where the
You lost your sound, John.
Oh, probably because I was covering the microphone. Can you hear me now?
Yep.
Okay, I better be careful about how I hold. I bet you if I turn this upside down, it'll actually be much better. Actually, it's probably better in like every way. I'm gonna hold it this way instead. Oh, that's kind of unfortunate that it's like that. Oh well. Okay, so 8 times r to the n, right? So yeah, so for any geometric series, the sum is the first. I shouldn't even write it like this. A geometric series, right, is something like this, right? Where there's some first term, whatever that first term might be, and then everything after that is some, common ratio times the previous term, right? Well, we know that that converges in some cases, right? In particular, when r is less than 1 or between -1 and +1, and it converges to this. So that is a formula that you need to be familiar with. For a geometric series, in general, it is extremely difficult to tell the sum of a convergent infinite series. But for this special type, it is quite easy because there's a formula. So it's whatever the first term was divided by 1 minus whatever the common ratio was. So in the case that it converges, right, in this case it was the first term would be whatever we get when we plug in n equals 1. So the first term would be negative 1/2. And then it's 1 minus the common ratio. And the common ratio in this case is also negative 1/2. So we could just work this out in particular, and that would be negative 1/2 over positive 3/2. And if you can really multiply by the reciprocal of that, and so it's negative 1/3. So in this particular case of x equals 1/12, I can produce the specific sum of this series. I'd better plug it in actually. Oh, well, that's on the wrong side now. Whatever, it's fine, we're almost done. So as you can see, Brian, it's not 0 or 1. In this particular case of x equals positive 1/12, the sum is negative 1/3. And indeed, it depends on the value of x, right? Depending on what you plug in for x, this series is going to work out to be completely different. Even in all the values where x is convergent, it's going to work out to be completely different.
It's strange though, because the question find those values of x only gives one entry.
Right, so I think what they were after was an expression of x.
I got you.
So an expression of x where if you were to plug in 1/12, you would get negative 1/3. But if you were to plug in, 0, for example, you would get 0, surely, right? If x was 0, that would literally be the sum of 0, and that would be 0. But it depends on the value of x. So all we got to do is just leave x alone. So just leave x alone. This is, you could write it like this if you wanted. I might prefer that. So just leave x alone. See that this is a geometric series, which means that if this is convergent, then it is equal to this formula, right? The first term, so the first term, whatever you get when you plug in n equals 1 would be that, divided by 1 minus the common ratio, which is also negative 6x, right? Since that's what you're multiplying, to get from, negative 6x squared to negative 6x cubed, you're multiplying by negative 6x. So negative 6x over 1 plus 6x is an expression which, for any value of x for which it's convergent, you can plug in that x value and it will just spit out the sum. So for example, if you were to plug in x equals 1/12, this would spit out negative 1/3. And if you were to plug in x equals 0, it would spit out 0. So in general, for any value of x that's inside the interval of convergence, if you plug it into this formula, it will tell you the sum of the series for that value of x, which is always changing depending on x.
Always makes so much the answer.
Yeah. So it turns out that you might say this. This adds up to this finite expression for x. You might write it like this. Right, for x inside that interval, the absolute value of x less than 1/6, or when x is outside that interval. So that's the situation. Okay, let me turn this upside down again. Put it back in here. Whoops. So I hope that makes sense. I hope that makes sense, everybody.
And did you say you're having some time on Monday as well?
Sorry, can you repeat that?
Did you say you were gonna have Monday?
Yes, yeah, Monday at I forget what I said. Monday at 5 o'clock. Monday at 5 o'clock will be our additional recitation session right before the exam.
Great. Thanks, John. Thanks, John.
All right. You're welcome, everybody. Hope that was helpful. Have a great weekend, and I will see you on Monday. Okay. Bye-bye. Oh, I was recording. Excellent. Okay. Stop recording. All right. Good luck on the exam, everybody. Bye-bye.